Harmonic Oscillator Lecture, Part 3. Let's go back to our sketch of the energy levels and the potential energy curve. We can go a step further, the risk of maybe crowding our diagram a little too much, and we can, so I've shown in white lines here the energy levels at E equals h nu over 2, 3 halves h nu, 5 halves h nu, and so on, this ladder of states, that ladder of energy levels that correspond to the harmonic oscillator. And then in blue, I sketched the potential, and of course where the white line and the blue line meet, that's the classical turning point. And we will return to that concept shortly. I've also, in red here, indicated sketched roughly what those wave functions look like that we were talking about before. As we go higher up in energy, the sort of width of the state in space gets bigger and bigger. And there are some things to consider about this shape of these wave functions and what they tell us. So we can also go to even higher levels. Let's just kind of assume that we've got some other level here that's way above these other ones at some very high energy and some quantum number v that's 10 or 20 or something. So we're going to kind of skip and then say we have our potential out here, and we've got an energy level here, say v equals 10 or something like that. Now the number of nodes, the number of zeros where the wave function passes through 0 is going to reflect the quantum number. Usually they're within 1 or so of each other. So the v equals 0 wave function that has no nodes, the v equals 1 wave function goes through 0, it has a node at x equals 0, the v equals v equals 1 has 1 node, v equals 2 has 2 nodes, and so on. And so for v equals 10, you would expect to have more nodes. The nodes are going to be piled up a little bit more, towards the middle and less towards the edge of the wave function. So it's going to look, there's going to be a lot of oscillations and not much probability density in the middle, and a fair number of oscillations. And then the wavelength sort of gets bigger as you get closer to the classical turning point. And I might not get the right number of nodes here. Let's see, I'm fairly close though. 1, 2, 3, 4, 5, 6. Yeah, so I've got an extra node in there, but roughly, so this would be like maybe v equals 12. And again, just kind of roughly showing what that wave function would look like. There's going to be more nodes in the middle and less probability density. And because there's often a rough correspondence between probability density, quantum mechanical probability density, and time averaged behavior. And of course, the probability density is the wave function modulus squared. So I sometimes say probability density and wave functions somewhat synonymously. They're closely related. They're not exactly the same thing. Once you have one, you can kind of get the other. So there's a rough correspondence between the quantum mechanical probability density and time averaged behavior of the classical particle. In that time averaged and then looking at it in probability, if you had a classical harmonic oscillator and then you stopped it at some random moment in time, you would expect that you would be more likely to have it stop near one of the classical turning points because that's where it's spending most of its time. Because that's where it stops for a moment. It slows down, it stops, and then it changes direction. And conversely, the classical particle on a spring spends very little time at the sort of x equals 0 equilibrium position, right? It sort of zooms past that. And so you expect to see, for classical probability, yeah, you expect to see this kind of parabolic behavior where it's spending most of its time near the edges of the turning point and less time in the middle. And similarly, we expect to see sort of less probability density in the middle and certainly more nodes. And we expect to see a peak in the probability out near, maybe a little bit to one side of the classical turning point. So we can kind of use this rough correspondence between quantum and classical to sort of guide our thinking. There's a couple of other, so that tells us roughly where the peak is in the probability density. Another issue that's not so much about the correspondence, but it's back to the properties of wave functions. Wave functions where the kinetic energy is high, we tend to see more nodes, right? In other words, shorter wavelength. So towards the middle, especially as we get to higher quantum numbers where there's more nodes. When you only have one or two nodes, it's kind of hard to see that this trend is not so apparent. But when you get into sort of V equals 6, 10, 20, that sort of thing, where you've got enough nodes where you can really start to see a trend, see that there are more nodes towards the middle where the kinetic energy is high. In other words, and where the kinetic energy is high is where the potential energy is low, right? If energy, you have some energy of the state, and in the middle of your harmonic well, the kinetic energy is going to be higher, and at the edges, it's going to be lower. And so, yeah, conversely, where kinetic energy is low, such as at the classical turning point, even though this is a quantum mechanical system, the classical turning point exists, right? You can still calculate it. Anyways, where at the classical turning point, and as you approach the classical turning point, longer wavelength. and fewer nodes. And then there were some other rules about wave functions and sort of sketching them, such that they should be, continuous functions, continuous valued. Otherwise, they're not going to be valid solutions to the Schrodinger equation everywhere. There's going to be discontinuities. And particularly if you have a smooth potential function, we expect our wave functions to be smooth. They're going to have a well-defined value, continuous value, and typically continuous first derivative and second derivative. So they're going to be fairly smooth functions, and then with if we couple these two rules, and we add the third, which is related to this first one, and the second one, where the kinetic energy is high. We expect low overall or low relative probability density. Because that corresponds to sort of the regions where the particle is moving quickly. And peak in the probability density, or the wave function squared. The wave function can have a negative value in these regions, but the square would be positive. So there we'd have a peak in the probability density near the classical turning point. And again, how near is of course somewhat of a judgment call for sort of v equals 0, v equals 1. It's not going to be so close to the classical turning point. As you get higher and higher, the sort of quantum classical correspondence is better. It's a better sort of approximation, and we expect to see more probability there at higher. We expect to see better agreement between the where we expect the classical probability to be maximum and the quantum probability to be maximum. But again, it's not exact, and but it's good to be able to compare and contrast. That's one of the things we do in science is compare and contrast. How is the quantum system similar to the classical system in some ways and different in other ways, and how does the quantum mechanical harmonic oscillator similar to the quantum mechanical particle in a box? How is it different? And so on, right? This is how we go about sort of classifying this menagerie or zoo of different systems. Okay, and let's see. So what else can we see? There's something a little bit odd in these curves, which is that it looks like there's some probability density, right? It looks like there's some wave function value out past the classical turning point. And let's look at that for a second. In fact, we can calculate the probability that the particle is outside the classically allowed region. Which is, of course, between the two classical turning points. And that, according to the Born interpretation, right, we know that the probability that x would be in a certain range, let's say the probability that it's greater than the classical turning point that's going to be equal to the integral from the classical turning point to infinity of psi star psi dx, where psi, this is for a given, say, state psi sub v. And of course, we know that these functions are have as a critical component, at least especially for v equals 0, is proportional to e to the minus alpha x squared over 2. It's this Gaussian bell curve. And of course, what do we know about exponentials? They have exponential tails. They fall off in a way reminiscent to radioactive decay, right? Where radioactive decay is not linear. It follows this kind of half-life type behavior where over some period of time, some of the molecules or some of the atoms decay, and you end up with half left. And then if you wait the same amount of time again, half of those molecules that are left decay, and so on, and you get this slow exponential, or this exponential decay. It never quite decays to 0, right? That's one of the properties of negative exponentials. E to the minus x, right? E to the minus kx or something like that. So then, based on what we know about exponentials, this integral is not going to be 0, right? We don't need to necessarily see exactly what that value is, but it's maybe 0.1, something like that. And so this shows. So this is greater than 0. It might be like 0.1 or something. Although don't for say v equals 0. We can yeah, maybe we'll do that calculation later, or in some homework or something. And what this is showing is that there's some probability that this quantum mechanical is found in this forbidden region, where you would never find a classical particle. A classical particle, if it has a certain energy, it's going to go up to the classical turning point, and then it's going to turn around. It's never going to go past the classical turning point. But for a quantum mechanical particle, because it's a wave, there's these sort of evanescent waves, and you get this quantum mechanical tunneling. And again, this is the kind of behavior that you expect to see with waves. You see this kind of thing in optics, like in the two-slit experiment. You see photons where they sort of classically, if you just had ballistic photons, they wouldn't appear, and they'll show up in these forbidden places. And so this is a manifestation of the wave property of matter, that there's this quantum mechanical tunneling, and we call it tunneling because it seems like there's this barrier, and it's like you're tunneling underneath it, right? Like prisoners of war escaping from a prison camp or something, tunneling out of the tunneling underneath the gates in some World War II movie or something. Anyway, so there's this quantum mechanical tunneling. This is a known, fairly general feature of quantum mechanics. And it contrasts with classical mechanics, with sort of Newtonian expected behavior. And So when you're comparing and contrasting, it's good to keep that in mind. And it's related to the fact that particles are waves, or waves are wave-like. They have this wave-like behavior. Okay, and now let's move on to, so we've talked a little bit about the shapes of the wave functions, and some of these rules are fairly generic, in that if you have some arbitrary potential, you can kind of look at each point in that potential at a given energy, compare the potential energy to the energy, that gives you the difference gives you the kinetic energy, and that gives you some idea of that there's going to be more nodes, shorter wavelength where there's a higher kinetic energy. There's going to be longer wavelength where it's lower. There's going to be a peak near any classical turning point. Okay, and another thing, sort of summarizing, recapping what we've talked about so far, there's this probability of finding a quantum mechanical particle outside of the classically allowed region. And in fact, this, and you might say, well, how do we know that? Well, you can actually, there's an effect on things like reaction rates. Quantum mechanics affects that. And there are numerous other examples of tunneling, like the scanning tunneling microscope, which involves electrons tunneling through a barrier from a sharpened, sort of a sharpened metal needle, or a carbon nanotube, and then that current is used to you use this tunneling phenomenon to get very high resolution microscopy images. Okay, so let's move on to expectation values. Right, so we have our energy levels, right? We have the spectrum of energy levels. We can sketch out an energy level diagram. We know roughly what the functional forms are for the wave functions, and that tells us roughly where the particles are, where they're spending sort of most of their time, and they're sort of giving a time average picture of where the particle is. So a probability that it's at a particular point in time, a particular point in space at a particular moment in time. And then the other thing that we're interested in is, sort of what are the expectation values for things like position and momentum. And that involves integrals again. So first of all, let's look, we're going to look at the v equals 0 state. And the full sort of algebraic expression for the v equals 0 state, including the normalization constant, which we kind of glossed over until now because it hasn't been important for, say, calculating the energy. But for expectation values, the normalization is important. And so we have alpha over pi to the 1/4. That's our normalization constant. And e to the minus alpha x squared over 2. That's our wave function. And that's the sort of functional part, the part that's a function of x. And of course, alpha is square root of k mu over h bar squared. So we're going to first look at expectation value for position. And in this case, all space does mean minus infinity to infinity. And we have psi 0 star. That's a real valued function, so psi 0 and psi 0 star are the same function. And then we have times x, and then times psi 0, and then our dx. Now here we can look at our system from a symmetry perspective. Psi 0 is an even function, and we have an integral from minus infinity to infinity. I think that's an important thing for this consideration of even and odd. You have to be dealing with either, there needs to be a symmetric integral over space, right? So it has to be, it can't be, say, in the particle in box case, it goes from 0 to a, so that kind of throws off our even odd function argument a little bit. We have to adjust it. But for this case, we're integrating from minus infinity to infinity, so it's a symmetric integral in terms of its range. And our function here is e to the minus alpha x squared over 2. That's this bell curve type function. It's an even function. And then, so even and x, that's an odd function, right? When you replace x with minus x, you get minus x. It ends up being negative, so it changes the sign. So this is an odd function with respect to inversion, with respect to replacing x with minus x. And the other function, and psi 0 is even. The product of those three functions is going to be an odd symmetric function, and therefore the integral will go to 0. So we can take that result, but also it's good to stop and think, does this make sense based on the shape of the curve? So we kind of think of the average position. It's sort of like the center of mass of this probability density curve. And you have this Gaussian type, this bell curve function that's symmetric and that's peaked at x equals 0. And so we expect that its sort of center of mass of this function is going to be at x equals 0. It's going to have equally weighted lobes on sort of either side of the x equals 0 sort of fulcrum point, right? So so we expect, yeah, the center of mass of this curve to be, or the first moment to be 0. Now let's look at, and of course we can also, it's not, this is one of those types of definite integrals that you could find in an integral table, or you could find something close to it. And you'll see that the integral table will tell you that the result is 0. If we look at the expectation value for momentum for position squared, that's going to be integral from minus infinity to infinity of psi 0 star x squared psi dx. And see, for this one, it turns out it's not 0, right? These are all even functions, and so we expect the integral to not be 0. And that makes sense qualitatively. This is like the second moment. This is saying, if we've got this Gaussian function, we expect there to be a Gaussian width. So there's a width to this, and we expect the width of this curve is not 0. So let's we have to actually set up the integral and evaluate it. Again, we'll do a little bit of simplification, but then we'll turn to integral tables, and we get see. So if we plug our functions in, first of all, we've got our alpha over pi to the 1/4. We have 2 of those multiplied together, and so we end up with alpha over pi to the half. And we might as well pull that outside the integral. And then we're going to have an integral. Let's see, we have sort of two copies or two factors of this e to the minus alpha x squared over 2. So e to the minus alpha x squared over 2 times e to the minus alpha x squared over 2. Basically, that's you're going to have, you add what's inside. When you multiply two exponentials, you add whatever's inside the exponential, and so that's going to give you e to the minus alpha x squared. In other words, we drop the divided by 2 part. And then we have times x squared, and the x squared is, well, we should probably move that in front of the exponential, but it's okay. It's just there, and then dx. So yeah, we can go ahead and move that there, and so we get we have this integral from minus infinity to infinity of x squared e to the minus alpha x squared. This is one of those ones, yeah, that you could find in a definite integral table, or you could plug it into, integral.com or Wolfram Alpha, or use Maxima or Mathematica, and it's going to give you an answer. And so the answer for this integral is we get 1 over 2 alpha times pi over alpha to the 1/2. Okay, and so some stuff cancels here because we've got this alpha over pi to the 1/2 out front, and so then we get that x squared is equal to 1 over 2 alpha. A very nice, neat result. So we expect, at least some fraction of the time when we're dealing with fairly simple functions, we expect to have nice, neat results that don't, it shouldn't be, 20 terms. So that's nice. Then we can also talk about what the width is of the position expectation value. And we said that this is 0. And so, the width is going to be 1 over 2 alpha. Now let's move on to momentum. And you remember our momentum operator is minus I h bar. We're going to drop the x. So this is one-dimensional problem, so we only have one axis. So we'll just say p. That's the momentum, not p sub x. Minus I h bar d dx. And so our momentum operator then is going to be our expectation value for the momentum operator is this sort of operator sandwich where we integrate from minus infinity to infinity of psi 0 star and then minus I h bar d dx psi 0 dx. And when we take the derivative of e to the minus alpha x squared, right, we'd be taking the derivative of the function to the right of it. So when we take the derivative of that, we're going to get a factor of x, right, because of the chain rule. And so this gives us something that is x is proportional to x times psi 0. And x is odd, psi 0 is even. And so this overall average momentum is going to average out to, our expectation value for momentum is going to be 0, sort of by symmetry. And let's stop and think if that makes sense. If we have a particle on a spring moving back and forth, Even classically, we would expect the average momentum to be 0 because half the time the particle is moving to the left and half the time the particle is moving to the right, and it's just going to cancel out completely if the particle as a whole is at rest, right? Unless the particle is, sort of moving through space, and if it is, that's a different problem. That's a particle in a box problem. So we'd have maybe a diatomic that's moving around inside a box, right? But we're looking at the vibrational motion here, so we don't expect any sort of net motion of the molecule through space, right? We expect just kind of local oscillatory motion. Okay, so that's 0. For momentum squared, that's going to be the integral psi 0 from minus infinity to infinity, psi 0 star, which is, again, the star sort of isn't strictly necessary, but you don't want to get in the habit of forgetting that these wave functions could be complex. We certainly will get into more complex wave functions in the rigid rotor, so we don't want to drop that. And our momentum squared operator is minus h bar squared d squared dx squared. Okay, and we've done that d squared dx squared business before, and we end up, when we plug that in, we get see, taking into account our normalization constant, pulling the h bar squared out front, we're going to get h bar squared alpha over pi to the 1/2 integral from minus infinity to infinity of alpha minus alpha squared x squared e to the minus alpha x squared. Again, so I sort of skipped some steps. I definitely encourage you to sort of follow along and see if you get the same kind of result. I believe I've checked this. This is the, and I've also plugged it into Maxima and checked my results, and this is what I get. And again, it's very related to, I also pulled a sine out of this. But anyway, so this we've sort of done before. We saw the alpha and alpha squared, x squared terms come out of that. I'm not going to reiterate that. Then if we plug this into, so this can be integrated, and we end up with h bar squared alpha over 2. And that is for momentum squared. And again, since the average momentum is 0, then the momentum squared is equal to the variance, actually, right? So it's also going to be, this isn't always true, but when the average value is 0, then the momentum squared expectation value is equal to the variance, right? We saw this before, but again, it's not always true. So we get h bar squared alpha over 2. And so then we can look at the product, sigma squared, x times sigma squared p is going to be h bar squared alpha over 2, that's from the p part, and then for x, it was 1 over 2 alpha. Interesting. So the alphas cancel. We end up with a product that doesn't depend on the particulars of the system in terms of what's the mass, what's the spring constant. That all factors out. And we end up with, and again, that's a multiply, not a minus. And we end up with h bar squared over 4. Now we can take the square root of both sides at this point, why not? And we get sigma x, sigma p is h bar over 2. So this looks similar to the Heisenberg uncertainty principle. We said that Heisenberg uncertainty principle says the product of the uncertainty in x, in terms of the sigma, the uncertainty in momentum, given by its sigma, the product of that is greater than or equal to h bar over 2. So this says for the quantum mechanical harmonic oscillator, it's exactly h bar over 2, that product. Whereas the Heisenberg uncertainty principle says it's always going to be either greater than or equal to h bar over 2. Therefore, what can we say about this system? The harmonic oscillator, the ground state, the v equals 0 state of the harmonic oscillator is the minimum uncertainty wave function. Right, we're not going to necessarily prove that there are no other functions that give you this, but it turns out that, yeah, this is the minimum. So any other kind of wave function, and we'll see other kinds of wave functions, right? We already saw sines and cosines, or signs rather, for the particle in a box. That gave a uncertainty product, sigma x, sigma p, that was greater than h bar over 2. Here we have the minimum uncertainty wave function. We'll see for hydrogen atom and other things like that, that the uncertainty is also greater than h bar over 2. And so any other system is going to give you more uncertainty. So it's nice that we identified sort of the lower bound in the uncertainty. And that's a good stopping point for this lecture. Next lecture, we will go through some examples of applying the quantum mechanical harmonic oscillator to make predictions about the vibration of the vibrational spectrum of in the infrared of some molecules. And we'll also look at something called the vibrational isotope effect.